What is cryptocurrency? Cryptocurrency is an internet-based medium of exchange which uses cryptographical functions to conduct financial transactions. Cryptocurrencies leverage blockchain technology to gain decentralization, transparency, and immutability. How does it work? So what we have right here is a diagram. If someone requests for a transaction, it will be broadcasted to a P2P network known as nodes. Then the nodes will validate the transaction and the user's status using known algorithms. After the verification process, it is combined with other transactions to create a new block of data for the ledger. Lastly, the new block will be added to the existing blockchain that is permanent and unalterable. This makes the transaction complete.
Now that we know the process, let's dig deeper.
What happens if the transaction is complete? It will be known by the whole network once it is confirmed. Confirmation is a critical concept in cryptocurrencies. As long as it is confirmed, it is set in stone. It will not be reversed and will no longer be forgeable because it is now part of the immutable record of historical transactions called the blockchain. Miners are the only ones who can confirm the transactions. This is their job. They will take the transactions and stamp them as legit. Then they will spread it in the network. Afterwards, the nodes will be added to the database and miners will be rewarded with a token in cryptocurrency, like bitcoins. And now, we move on to cryptocurrency mining. Basically, since it is a decentralized network, everybody can be a miner because there are no authority to delegate the task. Satoshi Nakamoto, the inventor of Bitcoin, sets the rule that miners need to do some work to qualify for the task. They will need to find the hash, the product of cryptographic function that will connect the new block with its predecessor. Let's now tackle cryptography. For this part, we're limiting the discussion to only the basics and fundamentals of cryptography. We're going to understand it by using an example. So Shal wants to send a message to her friend Mika, but how can she make sure that the message received by Mika is not intercepted by anyone or any untrusted individual? So what Shal can do is to apply cryptography. In cryptography, one can tell the message has been encrypted but cannot decode the message without having the proper key. Unlike in steganography, the message itself may not be difficult to decode but most people would not detect the presence of the message. So it goes like this: create a plain text, then encrypt to get the ciphertext, then decrypt so you get the plain text. That's basically the process. Plain text to ciphertext is what senders do and what we call encryption. Ciphertext to plain text, what receivers do and what we call decryption. And there are a lot of different ways to cipher, but we'll just tackle the most commonly used substitution ciphers such as Pigpen, Caesar, and Vigenère cipher. First up is Pigpen cipher. In here, the letters are just replaced by symbols. The symbols are represented by the given table or figure. For example, we have this problem. The shape of the first symbol is to be found on the first table, which is I. The second symbol represents L. The third symbol represents O. The fourth symbol represents V. The fifth symbol represents E. The sixth symbol represents M. The seventh symbol represents A. The eighth symbol represents T. And the last symbol represents H. You just need to find out which part of the border represents the symbol. Next, we have the Caesar cipher. It's one of the earliest known and simplest ciphers in which letters in the plain text is shifted a certain number of places down the alphabet. We could say that there has been an offset -1, that's why it resulted to this. Let's try an example. Encrypt the message, this is fun. T represents W, H represents K, I represents L, S represents V, I represents L, S represents V, F represents I, U represents X, and N represents Q. Now let's try decrypting a message. So F represents C, D represents A, H represents letter E, V represents letter S, D represents A, U represents R, and F represents C, L represents I, S represents P, K represents H represents E, and U represents R. For encrypting, we just substitute letters, and for decrypting, vice versa. Last but not the least, we have the beginner cipher. It uses a simple form of polyalphabetic substitution. Let's practice an example so that we'll understand the steps. Encrypt the message, make it happen using our keyword mat. First, we mark out what number matches the letter in our keyword. For M, we have 12, for A, we have 0, for T, we have 19, and for H, we have 7. Then these numbers, we'll just put it above the message we want to encrypt. We'll just continue to repeat the sequence until it reaches the last letter of the message. So for P, we have 12, for T, 0, E, 19, and 7. Actually, these numbers represent how many times it's going to be shifted. So we'll add the number above plus the equivalent number. For example, we have M, 12 plus 12 is equals to 24. That brings us our first symbol, which is Y. For A, we have 0 plus 0 is equals to 0. That's why we'll just use the same letter. For K, we have 10, and 10 plus 19 is equals to 29. Since we only have until 25, we'll start with letter A again for the remaining numbers. And that would be letter D. For E, we have 7 plus 4 is equals to 11, and 11 represents L. So this is what we'll just do for the others. Same process. We'll just use the equivalent number of the given message using the table above and add it to how many times it should be shifted. The result will give the equivalent letter you should use when encrypting the message. So far, we have Y, A, D, L, U, T, A, H, B, P, X, and U. That's our ciphertext for Make It Happen. Next, we move on to symmetric cryptography. It is the earliest known cryptographic method known to man, and it looks like this. Next, what we have is asymmetric cryptography. In here, the use of one key cancels out the use of other, and this is what it looks like. Next, we have RSA algorithm. It's the most widely used and popular asymmetric cryptographic algorithm in history, named after Rives, Shamir, and Adelman. For step 1, I would like to use P is equals to 11 and Q is equals to 5. And to get N, we have to multiply P times Q, so 11 times 5 is equals to 55. For step 2, we need to calculate the totient, and this is its formula. We just substitute the given and then we'll get the answer. 10 times 4 is equals to 40. For step 3, we just need to list the relatively prime numbers that is greater than 1 but is less than 40. We will only choose 7 so that it's easier to compute. For step 4, we just need to get letter D using the formulas. We have to use Euclidean algorithm and back substitution. When you study Euclidean, the equation would look like this. The 40x is from the totient and 7y is from E, then equals to 1. Then we ask how many times 7 can be equivalent to 40, then we add 5 to balance it out. When we derive, the 1 in the parentheses is usually placed on the other side, while on the opposite side we ask how many times the number can be equivalent and add the remaining balance. For back substitution, 1 is our goal, so then we just change the position from the last equation in Euclidean, and the procedure are as follows. With proper derivation, the detailed solution will look like this. That's our last equation. From this point, we care about what is sitting in front of times 7. However, it's negative, so to get D, we subtract the totient and 17. That's our answer, 23. So this is now our public and private keys. Public key is 23 and 55 and our private key is 7 and 55. Now these ends our discussion, and like what Bill Gates stated, the future of money is digital currency. And for me, cryptocurrency is the perfect example because not only it has a decentralized network, but also we can now eliminate our fear of trusted third parties. Now here are some links where I got the information. I also included some video links so you can learn more if you want. That's all. Thank you for listening.